So, I mean, this is the end of the whole 2 days. So I tried to be quite general, but just in reflecting on the back of that last presentation, which is where our heads are at now, I think you might frame this in the context of me being a bit iconoclastic with respect to standards. One way, standards that I think have been advocated for in the past presentation, and in some ways, perhaps this is an attempt to frame the limits of standards. I'm talking about AI in design and particularly how AI relates to BIM, because there are some trends that are in common between both of them. Both, of course, aim for better and more reliable models. That seems obvious. The phrase "single source of truth" is often bandied about, but effectively, the general trend in AI, in any AI model, in any training, is to reduce error in that model, to make it as good as it can be. And to some extent, this presentation is to make a case from the point of view of design of other models, and particularly those of decentralization, which has come up a couple of times, I noticed today. So is the McLeamy curve, which I'll credit Paulson, actually, 1976, which was before McLeamy, I think, started talking about this. This is Paulson's drawing here. I think everyone's familiar with this, so I'm not going to go into too much detail, but I use it because I think we are familiar with it. And we know that it describes the notion, particularly in BIM and other cases, that we try to push our design intent earlier on or design output earlier on in the overall project phase, where it has more influence and costs less in terms of changes. But this diagram not only describes influence, but also describes the amount of uncertainty, of course. So in any project, uncertainty is high at the very beginning, and it decreases over time as we go on. So what we're doing effectively is to push our design activity to where there is more uncertainty. And of course, this is a potential benefit of AI. But just to give an example of some of the work, from my own experience, we do use AI quite uniformly right across that whole project timescale. So just a few examples here. Of course, pre-design. This is some work originally by David Hawkins and others, going back more than 10 years now, on in the pre-design phase of energy analysis of the variables the design variables that can affect energy use in an overall project. There is a lot of information on this sort of thing. Carbon Buzz, you can see the example of the Carbon Buzz website around that time, which gives you a good example of general energy benchmarks for types of buildings. But those sorts of things don't include the actual design variables. So what Hawkins and others were looking at was the effect of things like orientation on site, amount of glazing, and so on, the actual things designers can control. And it turns out that training a fairly simple neural network, they could use those variables to predict better than the standard energy benchmarks by about 25 to 40%. So it gives you some idea of where to aim your later design decisions. Into the design phase, a little example on computational fluid dynamics. This is work by Sam Wilkinson and others, which showed that you could, computational fluid dynamics obviously being a very computationally expensive process. It takes a lot of simulation to get a good result, or wind tunnels even more. Wilkinson trained a model, again, going back to 2015 and earlier now, on the output of previous computational fluid dynamics simulations, or you could use real data from wind tunnels and actual tests on site. But he showed that a neural network was able to predict the outputs faster and just as well as computational fluid dynamics, an actual simulation. So this obviously makes it much easier in the early design phases to do things in more or less real time. On the construction phase, of course, there are a lot of ways that we can use automated techniques in construction. This is a fairly extreme example. Giulio Bernaro's work on training an industrial robot to use a chisel. Of course, in this case, it's a very temperamental type of process that usually requires a lot of skill, manual skill, and so on, knowledge of the material, heterogeneous materials. But same thing applies to any kind of use of heterogeneous materials that don't necessarily conform to standards. Wood grain and so on, of course, is very different species of wood. These things have a lot of influence on the way the tools behave. So these things can be controlled. And then onto the later stage of project management. So this is work Scott Fang and others looked at asset management. And of course, this was sort of immediately before the current phase of large language models and image processing, the kind of things we take for granted over the past couple of years. But they were using slightly early technologies to do both the language processing and image processing to take the example or the task of assessing the condition of various building assets to automate that. And of course, the neural network could perform in terms of judgment pretty much the same way that a human can. Slightly more extreme example, again, from the post-project design phase is Gennaro Senatore's work on this adaptive truss, which you can imagine a state where the building is controlled by a machine. This is a case where the embodied energy of the steel that would normally go into a truss is taken out by using much less material, but using these actuators, which, as you can see here, are maintaining the stiffness of the truss when the actuators are on. Now, the point here is that those actuators, in terms of their overall life, use a lot less energy than the embodied energy that would normally go into the extra steel that you'd have to put into this truss to keep the stiffness. The other thing to notice, though, is there is a bit of a wobble here. When load is applied, it does bend down a little bit before regaining its stiffness. That's purely because of the anticipation of that load, which at this point was done reactively. So there's no anticipation of the load. You could do this with better sensing and effectively better AI to predict where the load's going to be, which means that the reduction of the stiffness is now an information problem rather than one of materials. In any case, those are just 4 examples that show that we can reduce uncertainty of a type over the course of the entire life of the entire design process. But there are different types of uncertainty, and there's a different type of uncertainty. I mean, that uncertainty we're talking about is effectively risk or effectively probabilities that we can ascertain. But there is another type of uncertainty. This quote by John Maynard Keynes from nearly a century ago talks about it. And he's talking about uncertain knowledge not being what's only probable. He says the game of roulette, for instance, isn't subject to uncertainty in this sense. The expectation of life is only uncertain, only slightly uncertain, and the weather is only moderately uncertain. So he says the sense in which I'm using the term is the sense in which the prospect of a European war is uncertain. About these matters, there's no scientific basis on which to form any calculable probability whatsoever. We just don't know. Now, of course, he was writing just after the Great Depression. The kind of uncertainty that came about then with respect to economic models, we've seen the same thing with the recession, the recent, a decade ago now, I guess, the same sort of thing. We've seen the same thing with COVID. Pandemics and economic collapses and things are the true types of uncertainty that he's talking about here. And he says the way that we deal with them effectively as rational, practical men, he says, is first of all to assume that the present is a serviceable guide to the future. Second, to assume the existing state of opinion, as expressed in prices and so on, is a correct summing up of future prospects. And third, to fall back of the judgment on the rest of the world. So these are practical ways that we go ahead, and they deal with uncertainty of the probabilistic type, but they don't necessarily deal with this larger type of uncertainty, the uncertainty that we sometimes face in design as well. Now, these are the things that an AI and machine learning model actually does. It finds a pattern, it fits that model to existing data, and it aims to minimize that error to make that model better fit. But that doesn't deal with the types of uncertainty that really are truly uncertain. It deals with the types of uncertainty that we have in what Rittel and Weber called a tame problem rather than a wicked problem. I think automotive has come up, automotive design has come up a couple of times today. That's an example, even though it's very difficult, it's an example of an optimization problem where we can essentially map out what it is we have to do. We can set it up in advance and we can run some sort of optimization or other routine to know how to solve that problem. Whereas in wicked problems, which is what we often face in architecture and planning, really complex ones, we can't define everything in the brief. And there's a lot of embodied knowledge that has to come into the process further on down when things become more and more certain. This is that uncertainty falling off over the time in the McLeamy-Paulson curve. So these are the types of things that are more difficult to deal with in that way. Now, just to give a few examples of those differences, here's one from a recent, the UK strategic white paper on AI. at near the beginning, it lists a bunch of scenarios in which AI has proven to be very successful recently. And these two, I think, are the first two on the list. One is that AI helps piece together the first complete image of a black hole. And the other one is that AI solves a decade-old protein folding puzzle. You may be familiar with that. That was work from DeepMind. Now, these effectively look the same. They're both scientific results from AI, but in fact, they're very different in terms of the sorts of problems they are. If you can imagine the AI protein folding problem, very, very difficult, of course. But once we've done it, we've got a case where we can examine it, we can repeat it, we've got proteins available, we can investigate them in the lab, and we can have some sort of confirmation of whether the problem has been solved. In the case of the black hole, however, we've got a very different scenario. We've got a case where this is, happened light years away and light years in the past, and there's no sufficient test or validation for what it's saying. Now, in fact, I'm simplifying this a little bit. This isn't exactly, if it were about making a picture of a black hole, it in fact wasn't. But if it is what they said it was, which was making the picture of the black hole, well, this is the kind of thing that generative AI does all the time as well. It makes very good pictures, and the only test of this sort of thing is really that they look good. We can't really ascertain by any other means whether they actually meet the requirements that we might need in design, particularly in a wicked problem. We don't have a ground truth with which to compare them. Here's another example of two very similar looking images, but coming from very different, effectively, theories of what's going on. These are both images of London, if in case you can't recognize it. The street map of London, you can see it's colored up as red, some of the major streets in London. These correspond very closely to the traffic densities on those streets. These are pictures of two different theories that predict, or two different models that predict the actual movement in London. The one on the left is a series of shortest paths, of optimal routes. So if you were to optimize your route from every point and to every other point in London, these are the routes that you would get. So the streets are actually the best, shortest paths from every point to every other point. The one on the right looks very similar, but it has no idea about the optimal routes. This is just done by a series of random walking agents who have some local knowledge of where they are, and they make the decisions immediately based on their local knowledge, how much the streets turn in this case. They come up with pretty much the same example, same overall result, but they have very different means of producing it. Just a better illustration of that second one. Start off with, at the top, agents pretty much evenly dispersed all around, and then over, in this case, about 20 to 30 iterations of them moving from street to street, they congregate on those streets in which we actually find more people as well. So they resemble the optimal routes, but they have no idea about what those optimal routes actually are. Now, the reason that is the case is that London, as a lot of other spaces are, is what we call intelligible, that those two things are going to converge on pretty much the same overall result. So the local tells you quite a bit about the global, in this case, the shortest, most optimal routes. But there are cases in which that intelligibility goes wrong. It happens to be the case in most of the cities we know, but it could possibly go wrong. And we should be aware of that when we're designing, because we don't want to design spaces that are unintelligible. But it's often very difficult to see whether they are or whether they aren't. The two examples that you can see here, the one on the left and the one on the right, are subtly different. They might look very similar until you look very closely, because the blocks of buildings are actually all the same shapes. But on the right, they're slightly shuffled around. And what you can see in the correlations down the bottom is that the local measure, in this case, the connectivity or degree of a graph, is very well correlated with the integration, the global measure, on the left, but it isn't on the right. The degree of that correlation is the degree of intelligibility. It's how much the local tells you about the global. But it's very difficult to see the difference. So if we're not aware of this correlation, how do we know what's valid? To go back to one of those examples I showed you before, which seemed very simple with respect to training a neural network to predict computational fluid dynamics, in fact, in going about this, it wasn't really that simple at all. This is a case of a problem where we couldn't immediately see the way to do it. And in fact, the first attempts were not exactly total failures, but not good enough for the design purpose. So effectively here, this is a first attempt in looking at using the global parameters of each of these buildings as the input to the neural network to train it up to predict the effect of the computational fluid dynamics. And you can see the errors reducing over time with training set size on the right. They do reduce, but they still are, upwards of 20% or so, which isn't, it's not good enough for design. Now, this way of representing things doesn't work, but another way of representing things, which is to look at the local curvature, and again, having, in this case, very local curvature, these are radiuses of about five mesh points away from any given point. This kind of representation of the surface actually gives you the results you want. And this is able to learn with a very high degree of accuracy what the output of the computational fluid dynamics is. But it's a completely different representation, a completely different model with completely different data. And often we can't see what data is important in the first instance. Another example, one way to think of it is as a paradigm shift, which we normally think of as being some massive once-in-a-generation thing that completely reframes how we see everything in a certain scientific field. That was Kuhn's definition of it. But I would say that these sorts of things happen at a much smaller scale all the time in design. Here's an example, just one, in which this is some work I did for Anthony Gormley years ago in this series of body expansion pieces, where you can see there's thousands of individual steel members here. My job was to determine what the algorithm would be to place them all before someone sets out to weld them. Very, very complex. The initial and what seemed to be the obvious algorithm for doing so, these are surface normals emanating from the surface of the body, perpendicularly to it from every point. And you can see some examples here where they were actually welded together, and this was tested out. Turns out that that doesn't work for a variety of reasons. We don't have time to get into them now, but a variety of reasons that's no good. But what does work is a different model. This is a Voronoi diagram, and this works extremely well at giving us the overall form that we want. Now, the point here is that these are two very different models again. So surface normals to Voronoi, there's no way of translating one from the next. They're completely irreconcilable with one another. But this is the kind of thing you change from one to the next over the course of a design process. Typically, this is done in various ways, in many ways. In this case, it was done by making an instance in the real world, actually welding it together to test out the model, and then going on and trying something different. They seem very similar in terms of the overall aesthetics, but one actually gives you the result you want and agrees with our overall intuition on many ways. But it's this transition from one to the next, this sort of creative leap, or this paradigm shift, if you like, that's really important. It's a different model entirely. So this larger sort of uncertainty, which we can't quantify, we can't put into a model in advance, suffers from these 3 points. There's no sufficient test or validation. We can't always see the pattern, and these paradigm shifts can often happen in design, where AI aims to fit the model better and better, collect more data, and so on. These sorts of approaches that don't help in these cases. In fact, one model isn't enough to do it. They're all solved by changing to a different model. So where does that leave us with respect to BIM? Well, BIM and AI can work even in these cases as well. The example I would give is that of Dimitri Stefanescu's work on Speckle, which came out of our Interchain project, again, about 4 or 5 years ago originally, which effectively, instead of taking the standard BIM and CAD approach of having a single central model, or even a federated model, where you have different versions that are parceled off, but a constant set of standards that we agree on, instead of that, you can have a system where you can have a much more distributed network approach, where the models are different and may not even be totally reconcilable. One stakeholder might have a model that can't be translated to another, but they can create a system that allows that particular connection, the particular link in the network to be made so that they can communicate effectively one to the next. This is a very different way of working. Now, this is a network. It's got no central hub. It's got a much more complicated arrangement, but sometimes it's necessary. We do need mechanisms, of course, for tracing the data, for ensuring responsibilities and so on. But thankfully, we do have the technology to do that. Machine learning is well suited. Blockchain and so on are well suited to this sort of way of working. And this is potentially what we need to pursue more. Now, I'm not saying there are no standards necessary, but this is another view. Perhaps it is the case that we've got multiple models toward the beginning of the project, particularly when that uncertainty is high. And in this case, we have to negotiate and manage those uncertainties. We have to have a case where we're more decentralized at the start. And then over the course, as that influence and as that uncertainty declines, we move toward a single model toward the end of the project. That's it for me. Thank you.